Hello. Hello.
Yes, sir.
Shall we start? Hello, Dr. Nida.
Yeah, hi, Dr. Shabir. Good morning.
Yeah, very good morning. Just we'll start within 2 minutes. I'll
Yeah,
just give you a very brief introduction about you, and then we'll switch over to you.
yeah. Just please give me 2 minutes. I'm going to test my slides.
Yeah, sure, sure.
All right. Thank you.
Fine.
Yeah, hello, Dr. Shabir. Could you see my slides?
Madam, previously it was visible, but just now it is again not visible.
Yeah, so that time it was visible, right? Because right
Yeah,
now I
yes.
closed it.
Yes. Yes, it is visible now, ma'am.
All right. Okay. Thank you.
Welcome. Shabir sir, you can proceed now.
Yeah. Uh, a very good morning, Dr. Nida Jafri. A very good morning to one and all. On behalf of Electrical Engineering Department, SCET, and our entire team of FDP, I warmly welcome our distinguished speaker, Dr. Nida Jafri. She is a consultant and project lead with an international non-profit based in US and managing renewable energy projects across the Southeast Asia region. She has completed her PhD from Taylor's University, Malaysia, with research title Utilization of Oil Palm Waste as Fuel Source in Direct Carbon Fuel Cell. She has completed her master's degree from the University Putra, Selangor, Malaysia, and BTech from Integral University, Lucknow, India. She is an experienced researcher with 7+ years of working in analytical chemistry labs and 6 years of experience in teaching chemical engineering based courses. She has technical expertise in interdisciplinary research in chemical science and chemical engineering, including all fundamental aspects of material that involves their synthesis, properties, and how this leads to tunability of the material. She has technical skills in biomass valorization, biocar-based material for energy storage and conversion, pyrolysis technology, fuel cell design and fabrication, fuel cell performance and characterization, electrochemistry for energy applications, and combustion of alternative solid fuels for renewable energy production. She has been in charge of project management, proposal preparation, budget allocation, experimental design, data analysis, standard operating procedure, equipment purchase, setup design, operation, and fact, uh, troubleshooting. She has strong uh, uh, English verbal and written communication skills, including the ability to design and develop a well-structured written material, excellent internet research skill, including the ability to gather, synthesize, and interpret large quantities of the information from the different sources. She has hands-on expertise at various laboratories. She has published number of research papers at various journals and conferences at international level. She is associated with many professional bodies, projects, and consultancies with various countries, and she has received number of awards and honors at international levels. Today, she will share her experience and knowledge on planning of the microgrid. We are very delighted to have you with us. Dr. Nida, over to you.
Thank you, Dr. Shabir, for such a warm welcome, and very good morning to all of you at SCET. I am really honored to be here sharing some of my insight into the work, especially on this session of planning of microgrids. I would like to thank you, Dr. Shabir and Dr. Hardik, for extending this invitation to me, and I hope this session is useful to you all. And I would like to just take the context of the projects that me and my team are doing so that you all get a better understanding of the work that goes into designing of these microgrids / mini grids and how the entire process takes place. And while I'm presenting, please feel free to pause me if you have any questions, any queries, if you need further clarifications. I would be really glad to answer all of those to you. So before starting, I would just kind of give you a short introduction of myself in just a few words and the work that I'm doing, so that you have a context of why I'm here and what kind of work that I'm doing. So I am working in the capacity of a consultant with an international non-profit organization which is based in the US. And this is a green empowerment which collaborates with partners across regions of Latin America, Southeast Asia, and now we have expanded into East Africa. And basically, primarily, we develop projects related to renewable energy and clean water systems. And especially for renewable energy projects, we are trying to develop those projects which specifically target rural communities, remote communities, and we are trying to bring in microgrids into their space so that they get affordable and clean energy access. So yeah, with this, I would just like to start my presentation. Can you all see my screen?
Yes, it is visible.
All right. Okay. All right. So this would be the session agenda where I would talk about a brief overview of the microgrids and what methodology it entails, especially on the projects that we are working, and what are the planning tools and what are the approaches we use, what kind of toolkits we are using in our current projects, and how does the projects are implemented into these communities and villages. And obviously, along the way, we would discuss what are the present challenges that we encounter during the entire process. So like I said about my organization, I would just give a brief round of the introduction about green empowerment. So we have been working in this field for about 20 years. And like I said, we basically operate in Latin America and in Southeast Asia. We cover around 9 countries, and now we have expanded our work into East Africa. So the way we work is that we partner with different organizations across these regions, and we help those partners, which are essentially our implementing partners. And they implement the project, and we give them we provide them with technical expertise, strategic guidance, of course, funding. We help with proposal development, project management, and then, in collaboration, we are trying to establish our projects. So this is a brief intro about the organization that I'm working on. And we are trying to target the SDG goals. And 3 of the big boxes on the top are our main goals, we try to achieve these main goals through our projects, which is again affordable and clean energy access, clean water and sanitation. And like I said, we partner with different organizations, local organizations, community organizations. So our partnership is also strong in this area. So now jumping on to the main session, I'm sure all of you may be knowing what is a microgrid slash mini grid, as sometimes we refer it to. I think it's just a question of semantics. In the developed nations, it is more referred to as a microgrid, whereas in developing nations, people like to call it as a mini grid, but the work is same, the meaning is same. So microgrid is like a small consolidated grid system, like the national grid that we have, which supplies us energy that reaches our homes, right? So these microgrids slash mini grids are designed for smaller communities, smaller villages, who have people living in extreme energy poverty. So that means that they have very less access to electricity, or in some cases they don't have any energy access at all, which also means that they are living in remote areas, remote regions, where the possibility of the national grid to arrive is near to impossible. So in this situation, microgrids come into play, and they kind of take up a good role of supplying access to these a group of localized customers, and it operates in the same way as a national grid. So it's kind of a system where it uses the local renewable energy sources. It could be any of the sources available locally. It could be solar, it could be micro hydro, or it could be a hybrid system as well. And then it kind of builds its distribution and transmission system. And it has components of loads instilled into it, and that kind of processes the electricity to the households.
Hello, Nida. Sorry to interrupt you. Is it possible to switch to the presentation mode, because some of the things are not clearly legible?
All right. Okay. Okay. Is it fine now?
Yes, that is better.
Oh.
That is better.
All right. So again, talking of the microgrid, we can say that it's an integrated system of various interconnected loads, and it works on distributed energy resources that could supply electricity to a localized group of customers in a community, or in a couple of households, and that could also be attached to productive end users, which means that it can also support their income generating activities, their livelihoods in a much larger picture. And they also have the ability to scale up. So in the coming years, if we expect the community to be growing, let's say in 5 or 10 years, we can always put that assumption and put that logic and scale up these systems. So the next pertinent question is, why do we use microgrids? I mean, what's the benefit of these microgrids? So the first and foremost benefit is that they improve this energy access, especially for communities which are living in remote areas. So they can be living inside rainforest, they can be on top of a mountain hill, they can be living on secluded islands where electricity access is very low, and so these microgrids can reach there. And obviously, they are an alternative to our diesel-based generation. They have environmental benefits, and they could create local jobs if the community is empowered to be the main beneficiary. And if the community has control over these microgrids, they help to create jobs as well. They support their commercial activities, their livelihoods. And yeah, so they come with a variety of advantages. So obviously, when we talk about the opportunities, remote locations are the best way where we can really use this opportunity of microgrid installation, and they are part of the solution now when the climate change problem is on a high. We are trying to minimize energy poverty. We are trying to increase access to clean energy. So these microgrids / mini grids are a very good option, and not only in remote communities, even in urban areas, people are now trying to have this off-grid life, where they're trying to limit their energy consumption and trying to use the locally available resources. And the biggest technology drivers for this technology would be the high cost of diesel, and because the cost is so high, obviously the initial capital investment is high, then the cost of maintaining and running the system is high. So that all amounts to quite a lot. And with the declining cost, lower cost of solar PV equipments, and if you talk about micro hydro system, if these systems are manufactured locally by the community people, then the system cost, it reduces significantly. So that is a big driver as well. So coming on straight to the methodology, I would like to give you a context of the work that we are doing in our organization. So it will help you hopefully get a better context of the work that initially goes into designing of these and planning of these microgrids. So let's say if we are working on a project which says that this particular state in this particular country has about 200 unelectrified communities or 200 unelectrified villages, and we have been given this task of providing affordable clean energy access to these communities by utilizing the local available energy resources. So the first initial challenge is that how do we find out those locally available renewable energies, and how do we incorporate those into the project so that it obviously improves the livelihood of those communities, and that project, that work is sustainable. So which means that we are always looking out for a long-term work, let's say 10, 15, 20 years, so that by that time the community is all equipped with the expertise and they can all handle the work. So that is the initial challenge, and the general goal, I would say, is that because these are kind of new age technologies that have come into place, so how do we make these communities get acquainted with these technologies? So the point here is that we don't just go to these communities and give them the technology, right? We want them to become acquainted with the technology, to know how the technology works, to get a better understanding of the systems, to get a better understanding of the advantages of these off-grid systems, and then only we try to establish this partnership, this relationship with the community members. We try to give them, help them with technical expertise, so that in the long term, they are the sole owners of these systems, and they are able to manage it within their communities. So building these local capacities, it helps a lot. So there's a lot of discussion, a lot of troubleshooting goes before even we start the project. Everything has to be outlined, and the community has to be involved with the process. And, because they are the ones who have a lot of knowledge about their local resources. They are the ones living there, so they know much better than anybody else. So let's say if, coming from the same point, we want to develop this project with 200 communities, 200 unelectrified communities. So how do we go about doing this? So for example, we are doing this project here in the Malaysian Borneo region. which is the Malaysian Borneo region is the third largest island in the world, and there are a lot of remote communities living in areas where the national grid could never reach, or the state agencies sometimes say that it would take another 10 years, and every time they keep on extending this number because they are so remote. So we are doing this project with the state agencies here, and so the first step is trying to list down all these villages who don't have electricity access, or who have very less electricity access. Let's say they only get about 2 to 4 hours of electricity. Some rely on diesel gen sets, and maybe they are able to they are just able to get maximum like 4 hours of electricity. So we try to list all these villagers. We try to hold discussions with the state agencies, get into their records, and find out these villages with proper GPS locations. And also on the side, there's a big mapping team which does the work of mapping these these villages through satellite imagery process, and then we can see it on the map who are those villages which are very remote, or which don't have electricity. Then comes the second step of selecting of n number of villages. So this n number is like an open number, and it is based on our predefined criteria. So let's say we are trying to look at the remotest of communities. So the criteria here is remoteness. So the more remote the communities, they will fall under our project to help them get the supply, or they would be in the list of primary beneficiaries. So let's say we find out that out of these 200, 50 communities are very remote. So we try to pull out the GPS locations for these communities, and then our field team is being trained, especially on going to these sites, to these remote sites, and verifying that data. So sometimes it also happens that, let's say if we have this GPS coordinate of a particular community, and on the map it says it's a village, but many times it has happened that the researchers went there and they just saw an abandoned village, which means that people were living in that village, but they have already left the village, and sometimes it's like an open field, or sometimes it's like a graveyard. So it must have been a village, but it's now abandoned or turned into a graveyard, or just it's like an open field. So ground truthing is very important in this step, where the researchers go and they just find out whether there is an existing village or not. Once they have done that, then they are trained to do surveys. So in these surveys, we help the field researchers in drafting out the surveys, which means that, let's say, there are 50 communities, right? Or 50 communities or 50 villages. So they'll go, the team will go to each of these 50 villages, and they are going to talk with the village leader or the village head about the different set of questions that are drafted, right? So there'll be like a proper interview with the village leader. And then the next step would be interviewing all the households in that particular community. So let's say there are 20 households in one particular community. So the next step for the researchers would be to go into those households and try to hold talks with the members of the community. Or alternatively, we can also have focus group discussions, which are like discussions with three, four, let's say, men, or 3-4 women, or 3-4 youth belonging to that village. And then, they try to get an in-depth analysis of what is their situation like, day-to-day situation like, what is their livelihood looks like, what are their income generating activities, what kind of electricity access do they have, all those kind of things constitute this data. And then once we have all this data, then we start, analyzing the data, which means that we start looking into different drivers, different pointers that may point towards things that help us decide which technology would be would be useful for them. So that's like a pre-feasibility study. So let's say if the community tells us that there is a stream flowing in our community, within our community, or near our community, so that site may have potential for micro hydro power system. Or let's say if solar irradiation levels for that community are high, then the solar PV system would work, right? Or if they are both, then a hybrid system would work. And then the last step is obviously the feasibility study. So at this point, we've already decided, we already know what is the potential, be it micro hydro, solar, or a hybrid of these systems. So then the researchers would go into the field and do a full feasibility study, which is trying to take values and do calculations, and just drafting out the final picture of the project. So this is like the example of satellite mapping of some of the communities that I talked about earlier. This is what the mapping team does, and for this particular map, the criteria seems to be remoteness. So the criteria can be different. It can be remoteness, it can be an absence of a road, it can be the distance from the national grid, it can be different criteria. So this is how it looks like, and basis this, the field teams go out and reach these places and try to find out if the community exists there or not, and what is then the condition of that community. So like I said, now I would just want to list in detail about how do we create this methodology, especially when we want to create village profiles. So if there are 50 communities or 50 villages, then each of these village profiles have to be built individually, because every community is different from each other. We can't generalize that, okay, if one community needs are this, then the other would also be like this. So we have to make it really a case-by-case basis. So obviously one respondent, who is usually the village leader, would answer our questions, the questions that are in the questionnaire. These are just some of the examples of the kind of questions that we put into our questionnaire. The questions can be somewhere between 200 to 300, because we do an in-depth analysis, and it could range from questions like, when was this community established, what is the population size, how many households are there, is there any conflict on the land, or if there's a stream, what about the water rights of the stream, is there any conflict on that, and what are the amenities or utilities available in their community, is there a presence of school, or is there a clinic, religious spaces, and what is their socioeconomic status, the livelihoods, all of these things. Then once we have the data from the community level, we go down into at the household level. So let's say one community has about 20 households. So the researchers would go into those 20 households and get the data from another set of questionnaire. So that would be a little bit in depth, asking about their livelihood and what are the income generating activities, how much do they spend on electricity generation, what kind of access they have, are they using diesel gensets or not, what appliances they use in their homes, and if they're able to get electricity, what are their aspirations, in the sense that what kind of appliances do they want to see in their homes. So it also boils down a lot to their day-to-day activities. Let's say if the main income generating activities are fishery, so which means that the members catch fish, right, and then they go to the market and sell it. So at this point of time, then for them, having a freezer becomes really important, and we can't ignore the fact. So when we are analyzing the data, we know that, okay, these are people who are into fishery. So for them, having a freezer in their household, or even at the community level, is important. So while we are at the stage of system sizing and inclusion of appliances, we know what appliances to include and what are the most important appliances at that point of time. All right, so once we have all that data, and while we are doing the analysis of that incoming data, we would usually know, while looking at the load profiles, while looking at the appliances they would use, while looking at their day-to-day activities, that how much electricity would one community usually use. So depending on the community, the state, and the country it lives in, the values of these households would range from about 80 watt to 120, or it could even go up to 200 watt. And obviously in larger communities where they're attached to productive end users, the electricity usage increases with these amenities. And it also depends on, as I said, on the country, whether it's a hot country or a cold country. So their usage would depend on these factors as well. So this is an example of a demand profile. Now, once we have that data, we have to create these demand profiles for each of the communities so that we know how much is their power consumption, throughout the day. When do we see a spike in the power consumption? What is their, obviously, energy consumption? What is their usage looks like? So, for example, for this load profile, we can see that in the morning, the consumption is light, which would probably mean that they use light bulbs and fans, and probably some kind of appliances for preparing their food. While during the day, the use is minimal, which kind of tells us that the members are out for work, or they're in the field doing their job, right? And when they come in the evening, there's a spike in the consumption, which means that they're probably using appliances like TV, or they are busy preparing food and using those food appliances. So this is how we create load profiles for each of those individual communities. And before going on this demand profile, how do we get this demand profile? It's something like like a spreadsheet, which could also be a simple Excel spreadsheet, or it could be like a toolkit, or a tool which helps us do this analysis. So this is just an example of a simple Excel spreadsheet. We try to differentiate the household loads, the loads into different categories. So it may fall into the household consumption category. It could be for the community buildings and spaces like schools and religious spaces or clinics, or it could also be attached to commercial users, which entails productive end users, if they have any kind of activity, business activity going around in their homes or in their community. It could be rice milling, it could be, preparing of spices, grinding of spices, so, a spice miller, all of those things. And then we try to calculate the wattage of all these different appliances. So once we get the wattage, we know that, okay, we know that, okay, this is the consumption based on the number of hours they're using. So when we multiply the wattage into the number of the duration of the time, we can get the energy units in kilowatt hour, and then obviously we can find out our power consumption values. We would know that, okay, in a particular day, this community would use this much of energy units, and this much would be the power consumption per day, per month, and per year. So that's how all this is created. So this is just an example of the power ratings or wattage of different appliances. And this is how we try to list down all the appliances that those communities are using. And once we have this built, we know that this would be, these are the typical ratings for these appliances. So, so now let's come on the load management part, because while we are creating these demand profiles, load profiles, and there are a lot of communities involved in this. So let's just say if one community has 20 households or 30 households, and all the households will have different appliances, right? So the standard systems, when they are set in place, they might not account for this overload or a spike in power consumption, and maybe during off-peak times they would be underutilized. And so what is the solution for this? So especially for this load management part, we kind of build smart devices. We are in the process of building smart devices which would get attached to these systems and which would communicate with the user. So let's say if in a community, one of the households, the member of one of the household wants to use a washing machine for their laundry purpose. So it also might happen that many households would use the same laundry, the same washing machine for their laundry at the same time. That can cause a spoilage to the system that would cause overloading, of course. So what happens is when we instill these smart load management devices in their homes, these devices communicate with the user. So if a user wants to use the washing machine for their laundry, what do they do is that they go to that system and they press the button for the washing machine. And at that point of time, they would know that whether there is capacity in the system to let them in and use the washing machine or not. If there is capacity, they can use it, and a time would be fixed. So let's say each wash takes about 30 minutes. So the time would be fixed, and they can see the timer that, okay, for this purpose, for this activity, I have 30 minutes, and I have to, I have to use this time. But let's say if there is no capacity, then that customer, that user, would be held up in a queue. Let's say, after there is capacity, the user can use the appliance or whatever activity they want to use. So in this sense, the users also get conscious about their energy consumption needs, energy consumption requirements, and we don't we try to protect the system with these smart load management devices. All right, so this was about the methodology of the first phase. Now, once we have these load profiles and we have kind of identified and classified our loads, we know what kind of appliances are being used in these households. We come on to the demand estimation tool. Some of the organizations use it, some don't, but I'm just giving my example. Like, we are using this demand estimation tool, and I think it's very important because when we are planning for these microgrids/mini grids, we don't just plan for the short term. We want to target for the long term. So let's say for the next 10, 15, 20 years, we try to estimate how the community, how the village is going to grow, right? And these tools are very helpful in terms of giving us an overview of how the profile would change in the coming years. And we can also use these values. I think using these values for system sizing and system development is very important. So once we use these demand estimation tools to plan for our microgrids for, let's say, 10 years, right? So the next step comes on, next big step comes on to the cost analysis of these microgrids, because these projects require big investment, and especially when we are talking about so many communities, like 50 communities, 100 communities, and we are trying to scale up. So this requires a lot of investment as well. So we just don't want to start the process then and there. We have to analyze the whole processed, especially in terms of cost. We have to do a financial analysis, and we are using this Homer Pro software tool. Homer stands for Hybrid Optimization of Multiple Energy Resources. It's a software tools which was developed by the NREL lab in the US, and it's quite a popular tool. And one of the most important analysis that we can do is the cost analysis. So we would know how much this particular system of this much capacity, let's say 25 kilowatt or 50 kilowatt, would cost us in the specified amount of time. So if we have put 10 years or 20 years, we would know what would be the total net present cost of running that system, or the operation and maintenance cost. And because these systems are off-grid systems, so we also want to give an overview of and comparison with the traditional conventional diesel run systems. So we try to do an emission analysis, which of course is nil in our case. But with the diesel gensets, there are emissions involved, right? So we try to give a comparison between these two different systems, and this is important, especially when we are at a time trying to build up proposals for investors, and they like to see these figures. They like to see the financial figures. They like to see the comparison with the diesel gensets and traditional diesel systems. So they like to compare, and so these tools help us do that comparison. And obviously, coming now to the renewable fraction. This is also an important aspect, because some investors, some funders would want to specify the renewable fraction. They could say that, okay, we want the systems to have, let's say, 75% penetration or 80% penetration. So we can tweak these values in Homer software tool as well. Now, I've just put this as an example of the interface of Homer Pro, how it looks like, and this is where I'm working right now. At the moment, this is my my area of work in one of the projects that I'm working on. So if you see the big square, at the very left-hand side, you can see the electrical load, right? So it is the electrical load for the entire day, and we are able to tweak these values. We can input our own load profiles over here. And once we input these load profiles, we can see the daily profile of a particular community. And we can see that, the load profiles, how do they change during the day, and in the evening we can see that there's a large spike, so which means the power consumption is high in the evenings, and also it can give us a seasonal and an yearly profile as well. So the way it works is that, let's say we are working on hybrid systems, so we have micro hydro and solar involved in our distributed systems. So we first have to build the schematic, which means that we put in the components in this modeling exercise. So you can see that we have the micro hydro component, we have the solar panels over here, and obviously we have the battery storage component, the converter, and whatever components the project entails, we can put into these into the schematic, obviously specifying their specifications. And this also comes with an option to attach it to the grid. But right now we are not looking at grid connected options. I've just put it as an example of the work that it can also do if we want the grid to come into the picture. So once we input all these components into the schematic with their specifications, then this Homer Pro software starts to simulate the profiles for these communities, and it works on kind of it's like a database toolkit. So it starts to simulate and extract values from thousands and thousands of data sets that are already stored in its library. So it gives us the best option the system that we want. So let's say if there is a site where we are not sure of what kind of system would work, so we can go with with micro hydro components, solar components, and even we can include wind components. And then the software will tell us, after doing those numerous simulations, what kind of architecture is the optimum in our situation, especially in terms of cost. So we can see the optimum values and optimum architecture for our range of specified values. So this is how it looks like at the end. Once we are done with simulations and our modeling exercise, we can see that the annualized cost of these components. So in the left-hand side, you can see it's written annualized, right? So which means that we can see the cost of these different components on an yearly basis. So which is about, you can see in the end, these are the components, and you can see that the total capital cost, which is the initial capital cost, amounts to about $7,000, which also we can see in the bar graph over here. And yeah, so we can have this, visualization of different aspects, be it operation and maintenance, replacement. We can see all these individual costs. And so this really helps us put these figures, in our proposal, or if we have the investment, we have the funding, we can start with the next step of the project, which is project implementation. And the second row that you see at the bottom, it's also quite an important visualization of the results. In terms of the metrics, we can see that this is the NPC, which is the net present cost, which typically means the cost of the entire system for the duration that we have specified. So let's say if I've put 10 years for this hybrid system, micro hydro and solar hybrid system, it would give me, it would incur a cost of this $241,000 US dollars for the entire cost of for the entire duration of the project. And this is COE, sometimes referred to as LCOE, which is the levelized cost of electricity, which typically means that this would be the cost of electricity per kilowatt hour. So if let's say the household is consuming let's say 50 kilowatt hours of energy in a day, or in a month, I'm just giving an example. So this would be the cost for that per unit of electricity consumption. So that is also quite important, and this way we can see that, okay, if we want to do an in-depth analysis on a household basis, we can also say that, okay, this household's energy consumption is this much, and in a month, this much would be the cost that it would entail going by its electricity usage. All right, so this was about the planning tools. Now, once we are done with our initial round of methodology, we are done with our planning. So now comes the project implementation. So for this part, I've just given an example of micro hydropower system. This is also one of the projects that we are working on. So hopefully the next slides would be useful in terms of getting a visual view of the work that goes behind planning of these systems. So traditionally, the approach has been that the design and the operation and the maintenance work, the management, all these roles would fall onto the team of experts or the technical team which is doing these projects. But with these community development projects, our approach has been co-construction, or co-designing with the communities, which means that with aspects of design, operation, and maintenance, we try to We try to be in talks with the community members. We try to get their views, get their inputs, and then only we try to, design the systems. Because as I said, they always have better understanding of their local resources, of their local land areas. So their input is very important. And if, let's say, they don't have the technical expertise, which especially falls under this operation and maintenance part, then we also try to help them with technical expertise. We try to build their technical, we also try to build their local technical capacities, and we try to train them so that in the coming years they're able to manage the system on their own, and they don't have to fall back on anyone. And they just take up the role of that ownership role. So they are not only the beneficiaries, I mean, they are also the people who are playing an active role in the process, right from start to the end. So for a microhydro project, generally the first prerogative would be for the community to have a water flow body or a river stream in the community, or nearby the community. And we kind of do the pre-feasibility study. We try to do the feasibility study. We get all these values and calculations, especially for the flow of the stream and the head losses, the efficiency, and all of that. And then we try to identify all the paths that would be incorporated into the system. We try to estimate the power that would be available. So if the stream flow is high, the power would be high. But let's say in seasons where it is a dry season, the stream flow, sometimes the streams would dry up, and they would be a decrease in the water flow, right? So that would affect the power as well. So all these considerations we have to keep into mind, and then only we can estimate the power output of coming out from that system, and whether it would suffice the community needs or not. All right, so the nomenclature goes by this by these terms, and in the Malaysian Borneo region, we are trying to work with microhydro power systems, which range typically between 10 kilowatt to 100 kilowatt. And the one that we are working on is a 60 kilowatt system. And yeah, so this is just giving you a reference of what the capacities look like. Now, this microhydro system is like a run-of-river configuration, which means that it kind of uses the flowing water, the kinetic energy of the flowing water, and then changes it into electrical energy for power generation. So if you can see it from the figure, the weir is like a barrier that kind of diverts some portion of the stream of the water flow into a channel, right? So also before designing these processes, there are regulations. We just can't we just can't build up a barrier and kind of divert all the water from that stream. There are regulations to it. So I think it's about 70%. We can't go beyond 70%. So 70% of the water we can divert for the installation of these systems, for the setup of these systems. So once this weir diverts the water from the river stream into this channel, the channel kind of brings it into a forebay, which is kind of a reservoir of water. And from the forebay, there goes this penstock pipe, which is like closed steel pipe, which transports this running water into this powerhouse, right? And there is an elevation, if you can see. So this is what the head is. So if the elevation is high, the head value would be high, and it directly translates into a higher power. And in the powerhouse, we have our turbine and generator housed in, which kind of uses the kinetic potential of the flowing water and converts it into electrical energy. And then that electrical energy is kind of transmitted with the help of these heavy cables, which are transmission lines. And these are then further distributed to the communities. So this is just these next slides would be just to give you a brief overview of how it looks like into one of these communities, what is the process, and how do we come up with the design, of the system. So like I said, you can see the weir, it kind of diverts the water into a channel from where we can harness the water for our use, and the water flows into a forebay. Then there's also a catchment area, so it means that we can also use that water to test for to test the rainfall health. We can also use that water for some other agricultural activities. So that is like additional thing, but not all micro hydro systems will have catchment area. Now, obviously, once the water is diverted from the weir, it goes into a channel, and then it enters an intake from where it passes through a channel and goes into the forebay, and then comes into the penstock. So this is like a path created of concrete, and you can see there is a lot of civil works that goes into the designing of these systems. Now, additionally, sand traps are also made out of concrete. It is like a tank where, it traps all the fine sediment and, the fine clay and the sand of the water, so that we get clean water for our use. There is also this creation of spillway, which is also created as like a sideway, which kind of allows excess water to flow back into the river. So if there is an overflow of water, it just goes back into the main river stream. And sometimes there is this combination of forebay and silt reservoir or tanks, which are built together, and it just does the work together. And it is also, it's also built out of concrete. And if you can see over here that just before the forebay tank, there is this sluice gate, which allows for so this is another mechanism of allowing for cleanup of the water with before we take it into the tank, and before the water is used and goes into the penstock to be able to harness energy. So this is what it looks like. You can see that this is the penstock pipe, which is like a covered closed pipe, which transports the water from the forebay into the powerhouse. And there's this elevation. So the head value is like the difference in the elevation, and the higher the elevation, the more the water flows in, and the more is the pressure of the water. And down below is the powerhouse, which houses obviously the turbine and the generator, which generates the power, and which is then further connected to the transmission lines. So all right, so this is kind of another example of a powerhouse, and if you can see, this is like a tail race, which is usually once the work has been done, right, the water that passes out of the powerhouse, it can be diverted again to this channel, which is again built out of concrete, and this is called a tail race. So the water then flows through this tail race and joins the main river stream. So that is like, that water can be used again and again without wasting it. Obviously, this is the situation inside the powerhouse. We can see that there's a valve which regulates the water flow into the turbine, and we can set this according to the need. And once the water flows in, once the water flows in, the generator is combined with the turbine, and that generates electrical power, and then it goes into this control panel, and then it is transmitted to the cables, which are the transmission lines. So this is how the setup looks like. So it's as you can see, there's a lot of work, especially related to the civil works. So the partners, the implementers who are doing this, they have to make sure that the civil works, the electrical works are quite done diligently, so as not to have any issues in the future. So all these kind of things are done based on system design, and there's a lot of iterations done to the design and the system before it goes to the final. So we can use transformers also sometimes, and this is just transformers are just to step down the heavy voltage which is flowing across. So if the voltage is heavy, we can also install transformers to step down the voltage before it reaches the households. All right, so the question would be, how much electricity will the plant produce, right? So for the estimation of power generation, there are two main parameters that we look into. That is the head and the flow rate. So flow rate is obviously the flow of the water that's flowing in the stream or in the river, and head is that elevation. So so during the year, when when it is when the community is experiencing different seasons of the year, sometimes it's dry, sometimes it's rainy. So the flow rate may change, right? If it's a dry season, the flow rate would obviously be low, and if it's monsoons, rainy seasons, the flow rate will be high. So that is not a constant parameter, that will change, but the head, of course, will not change. It will be same. So these are two of the design elements that we look into, and we try to get the efficiencies around get the efficiencies based on these two values, and we try to have higher efficiencies, which would obviously translate to higher power generation. So just trying to wrap up this micro hydro system, the key points would be, it includes a lot of, as I said, civil works and electrical works, and these are these electrical poles and transmission lines, distribution lines sometimes. So that entails a lot of these works, and during the feasibility study, the calculations for head and flow rate are very crucial, and we want to make it we want to get those right. And we also want to account for seasons when it is dry, and we don't, we just don't want to look at seasons where it is monsoons and where it is raining heavily. We also want to account for the flow rate when it is dry season, so that we can know that, okay, this would be the minimum amount of power that this plant would be able to produce. All right, so once we are doing the project implementation, is if everything is okay, the project is implemented. But in ideal world, that is not the situation. The situation is quite different because apparently these microgrids and mini grids are not yet recognized by most of the central agencies, state agencies. And there's no explicit mention of these microgrids in their policy framework, in their regulatory framework. So there are a couple of different challenges that we face, and especially because we are so actively involved in these microgrid installations and microgrid planning with the state agencies. So we kind of know what are those barriers. So I've listed these barriers: technical, financial, policy, and regulatory. And so for the technical factors, obviously we are trying to cater to the community needs, right? And we don't want it to be an independent sort of system. We want the community to take the lead on that, and we want to co-design with the community. So many a times it happens that the communities are not well versed with these technological advances. They are not well versed with the technology, and versus they know how to use a diesel genset because that's the most convenient thing for them, for obvious reasons. They know that, okay, when the genset fails, I can always bring in diesel and start the system and access electricity. But that's not the case with these renewable systems. So a technical expertise is quite a challenge, how to build that technical expertise within the community, how to increase their capacities, how to make them well versed with these new systems, right? And if we talk about the system itself, the system is not, I would say these systems are quite sophisticated on their own. So especially if we are trying to build hybrid systems, so if there are different components attached, let's say if there's a solar component attached, so the use of battery storage becomes essential. And then these batteries are expensive. There is a technology that goes around maintaining these systems. So operation and maintenance also becomes a challenge. And it kind of, it kind of threatens the longevity and the continuity of these systems. For the policy factors, I think this is also very important, because so far what we have seen is that there are no policies that exist which explicitly mention the use of microgrids, right? And under policies, I mean that there are no special consideration given to these microgrids. They have kind of come under the umbrella of renewable technologies. And for renewable technologies, the government agencies are just focusing on solar hybrid systems, which are solar diesel systems, and they are not that willing to draft policies which talks about long-term subsidies. There are no such electrification programs that supports the needs for these communities through microgrids. And so these are kind of the policy barriers, and which is not existing for the traditional ways of electricity generation. So I think electrification needs have changed, and the meaning of electrification is constantly changing, right, with these off-grid systems coming into play. So if the policies are there, right, the system, the process, the planning becomes quite easy, because we know what are the institutions that are dealing with these microgrids installations, which are dealing with the planning of these microgrids, and we can go to these institutions. But in reality, those institutions don't exist. And obviously, there are a lot of challenges in their regulatory framework as well, which means that, as I said, that these microgrids / mini grids, they come under this umbrella of renewable technologies. There's no explicit mention of them as a separate entity. So that means that there are no standard operating procedures, there are no design standards, there are no quality standards, health and safety standards are not there, and it kind of if these things are not into place, it kind of also tells potential funders and potential investors not to invest in these kind of fragile projects, because there's a huge amount of uncertainty attached to these projects, right? Because it's not yet supported by central and state agencies. So if there is a kind of a system where there is a separate office or a separate agency which deals with the issues of these microgrids, and with the planning and the policy making for these microgrids, it will be really helpful, in the sense that whatever funding is coming, they are taking care of the funding, and they are giving this funding out to potential investors or potential funders, or even to developers who are expressing their interest into into developing these kind of projects. But the thing is, there is no such agency that is taking care of these factors. And within the government system, there is a lot of duplication of work, which means that um, one task is handled by different agencies. So if suppose a funder comes into play or a developer comes into play, they wouldn't know which agency to go to, right? And there are other issues such as ownership. So if let's say the situation, if let's say the system is installed, these systems are planned and installed, who takes the ownership, right? Who comes into play when there is an issue related with the operation and maintenance of these systems, or if there is a breakdown, who takes charge and does this work? So in many of the cases, in many of the cases that have happened, what eventually happens is that these systems, if they experience a breakdown, they just break down, and the community doesn't have that much expertise, doesn't have the financial capacity to kind of correct these systems. So they just leave them, and they are just there as discarded assets. So I think a sufficient system for these kind of for this planning for installation would work really well with these with these systems. And because we are targeting, most of the people are targeting these systems to be installed in remote communities where there is a lot of supply of renewable sources, where the renewable sources are abundant, right? So a lot of investors and funders, they're trying to take over in a good way, of course, and they're trying to build up systems which can support productive end users along with supporting the community demand. So if this comes into play, right, it's a very good move. It's a very good advantage to these microgrids and mini grids. But there are these barriers, and I think it's like a nexus of different actors. There are a lot of actors involved in this whole process, be it the community members, be it the developers or the funders, the state or the central agencies. So it's like a web of actors which need to come together for a successful implementation of these kind of projects. So one of the technical solutions right now seems to be a hybrid microgrid, which is a system where we kind of pair the system with diesel systems, and it operates in conjunction with the diesel operated systems. And so let's say if there is a breakdown, if there is a shortage, the diesel systems can come into play. And also, if you don't want the diesel systems, if you want it to be 100% renewable, we can involve different renewable components, be it wind, be it solar energy, be it micro hydro, and kind of add battery storage to the system, so that whatever excess energy is created, it goes and it gets stored into these systems for use later. So these are also kind of new age solutions that have come into play. And like I told you, smart microgrids with the load management techniques have also have now being used in a couple of the projects. And we are also working on some of the projects which have these load management devices which are installed in community homes, and they kind of interact directly with the users, and the users become conscious of their electricity needs, and when and what time are they able to use these devices? And of course, it protects the system as well. And while making sure that there is a constant, continuous supply of power. So coming on to almost the last slide, what would be the conclusions and the potential solutions? So especially when we are planning for microgrids, when we are doing this co-designing, co-construction with the community, we need to make sure that those community members are involved in the process, they are familiarized with the technological advances. And one very important criteria, I feel, is that while we are trying to create the load profiles, we are trying to estimate the demand, we should also look for the demand for the next 5 or 10 years, right? How would the community be growing in the next 5 to 10 years? So if today we are giving them electricity and they're able to manage their livelihoods and they're able to run their productive end users, then obviously that accounts a lot to them in the improvement of their livelihoods. And then in the next 5 to 10 years, there would be a sufficient increase in the growth in the demand as well. So system sizing is very important here, and the demand estimation is very important for the future. And the other thing that we need to take into account while we are planning for these microgrids is to create this local management structure within the community, which takes charge and is able to operate and maintain the system, right? Because these renewable off-grid systems, they require good maintenance and good care by the owners. So that is very crucial. That is really very crucial. And so if the management is strong, it would mean that the system would be up and running for the next 10, 15 years, and it would be a sustainable system. And like I already mentioned, that this process is like a huge process involving a lot of actors from different fields, be it the state agencies, even the central agencies, developers, the community members, funders. And so this creates a whole lot of big system. And so just defining a way where we can promote this strategic bonding between these actors, so that they all come to one point of place, and they all know that, okay, if we are to plan for these mini grids, we need to go to this particular agency and or this particular office, and we would know all the design criteria, the standards, the operating procedures, and kind of making it legalized for these microgrids to operate. Because currently, especially I'm talking in the context of Malaysia, these microgrids are not regarded as legalized. They are still seen as something illegal, or something which is not given so much of importance. So having this kind of partnership, bonding between the actors would really help. And lastly, obviously, because these systems are not cheap systems, they involve big investments. So a development of feasible business models where we kind of we ensure that the operating expense would be covered on time, and we would not run the system and this, with losses, right? So just development of these feasible business models based on our on the previous analysis of load profiles, demand analysis. I think that would really be helpful in this case. So with this, I end my presentation. Thank you for your attention, and we can open for questions if you have any.
Yes, participants, if you have any question, please raise your questions. I think she would be able to answer the questions not only about the theoretical aspects, but I think almost all aspects and the SDGs, those are defined by the UN in 2015. So they might be working on three main goals of that SDGs, that is 6, 7, and 17.
Yeah.
Some of you may not be familiar with this particular thing, that the UN has defined 17 such goals, that is the Sustainable Development Goals. And the sixth is about the clean water and sanitation. Seventh is, I think, related to the renewable and clean energy. So I don't remember exactly what the 17th is, but we've been working on the seventh goal of SDG, that is provide the affordable, I guess, affordable and renewable
Mhm.
and clean energy to the community and the society. So
All right.
she has well explained that thing also. And being this session, which is very closely linked, Nida is very closely linked and connected this, I mean, her discussion with our FDP title, that is Microgrid, a part to sustainability. Uh, and she has explained for a country like Malaysia, which is having a bunch of islands. So the
Yeah.
primary purpose of such formation of the microgrid or the nanogrid is to reach to the remote area. She has already talked about the places where the accessibility of the electricity is a big problem or challenging, like the countries like Malaysia and even African countries.
Yeah. Exactly.
So and where they can identify the households or the few bunch of households uh, 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 where they are living in the remote areas, and the laying down of the grid or the extension of the grid is very expensive task. So that has been very well explained, the planning of microgrid. And in two cents, what is the planning of the microgrid? Nida, just for your information, just before your session, we have talked about the planning of the microgrid, and in that there are certain aspects have been covered. I'll share that slides with you
All right.
uh, for your reference, and we would rather be happy to have any kind of the discussion, any kind of joint work with you and your organization. So
Sure. Sure.
I've also been working on the Homer since 5 7 years.
Okay.
So any comment from the participants, any question, because she has spent a very good time from her busy schedule. She has been working as a project leader for this particular microgrid and planning, even though she has spent some time, and she has accepted our invitation, and she has customized her presentation as per the demand of the topic, time allotted, the nature of the participants.
Thank
So
you.
any
Dr. Thank you so much. It has been a pleasure to come here and share my insight. Thank you.
uh, participants, if you have any question, very quickly you can throw some questions. Even later on, you can ask your queries, and we would be routing those queries to Dr. Nida.
So, I see one question. It says how to set the size of, sorry.
Nida, there is a question how to select size of the DG in Homer. So that is asked by Hetal.
So this DG is the distributed generation, right? Is it?
Are you talking about the diesel generator or distributed generation, Hetal?
Oh, okay. It says source. All right. So I'm assuming that let's say we are trying to build a solar PV power system scheme, right? So we will see the load profile of that particular community. And let's say we are trying to design the system and keeping in mind how the community will grow in the next 5 years. So the demand analysis tool that I talked about, we will input our parameters there, especially the growth rate. So we would know that, okay, the next year, the village or the community will grow by this percentage. The following year, it will grow by this percentage. So it kind of gives us the load profile, and we would know the load profile from there. So that load profile is then exported into Homer, and the capacity of the load of the component, it follows the load profile. Sometimes we can also, especially I'm talking about Homer's, so there is an option where we can step up this load size by 10%, 20%. But I think in Homer, it's already the factor is already inbuilt at 10%.
Yes, yes, it is a day by day, it is a 10%, even you can
Yeah.
change it 20%. So
Yeah.
ultimately that can be mapped to the future expansion.
Yeah. So this is actually quite a good question, because system sizing is very important. If we undersize the system, then it will not meet the community needs, and if we oversize the system, it would be obviously costly. So this is quite important criteria when we are designing the system. So I would say we follow the load profiles, and then we just take that value and size the components according to that.
Yes, any other question? See, as I had already mentioned in the previous session also, the load profile is a very crucial part of the designing of any of the microgrid, and it has to be meshed with the requirement, I mean the demand and the supply. If it is not matching, then you need to take some other factors into account, like storage of the system and the shifting of the load, or the peak shaving and demand side management. She has also talked about something like smart load management device, which may be taking care in actual practice or in actual scenario.
Yeah, exactly. When we're designing these systems, we have to be sure that these systems are resilient, and they kind of are sustainable for the long term. And the users, the people in the community are not that well versed, and and different households may use different appliances. Some may use power tools, which may consume a lot of power. Some may use different appliances. So we try to kind of balance the effect by the introduction of these load management devices.
Okay, so if there is no question, then we'll be winding this session up. Thank you, Dr. Nida, for your time and sharing your knowledge with the participants. On behalf of entire team of the FDP, entire team of the electrical department of Sarvajanik College of Engineering Technology, I'd like to thank once again for your time and the details that you have shared. You have already shared the presentation, so that will be shared among the participants, and we'll definitely look for any of the collaborative work in future.
All right. Thank you so much,
Thank you,
Dr.
Dr. Nida. Thank
You're
you. Thank
welcome.
you very
And
much.
again, I would like to thank you and the entire department at SCET for having me, and it was really wonderful to communicate and to have a call with you all. Thank you so much.
Thank you very
Yeah,
much.
thank you.
Thank you. Uh, Now, participants, it's almost 1:10. So if it is possible, then we would start the session by 2 p.m. So we can wind it up earlier. Hello.
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir.
So would it be fine to meet at 2 p.m. instead of 2:30, because it is 1:10? And at 2 p.m., if you feel that 2 p.m. is too early, then we can keep it at 2:15 or 2:15. So just let me know whether you are comfortable with 2 p.m. or 2:15. $2.15 would be fine. If Mr. Rakesh is in favor of 2:15, so let's 2 is also fine. Somebody is saying 2 is also fine. Okay, so majority, I guess the 50% are in favor of 2, 50% and other are in 15. So let's keep it 2:15. Let's keep it 2:15. And so we'll be meeting at 2:15. So at the 2:15, what we'll be having, we'll be having a feedback session first, and then the valedictory function. So we'll take hardly 5 to 10 minutes, and then after feedback and valedictory valedictory function, you have to appear for the test. The test would be of 30 minutes, and there will be 50 questions. The questions are drawn from the sessions that we have been conducted so far. Yes, time of test. Let's freeze the time of test to 3 o'clock, and from 3 to 3:30 there will be a test, and then after you will be free. Would it be fine? So let's keep the test at 3 p.m. We'll meet again at 2:15. We'll have 15-20 minutes of the feedback round. If you would like to share your view, I suggest to some of you to have the honest feedback, and then we'll have a 15 minutes of the valedictory session, and at 3 p.m. I will post the test, and that would be for 30 minutes. That there will be a 50 questions. Most probably there won't be any subjective kind of questions, but there will be objective and short questions, and then after you can leave the meeting. Fine. So we'll be meeting at 2:15. Thank you, participants, for your presence, for being with us, and we'll be meeting at 2:15 after lunch break. Okay. Thank you.